About buoyancy. Suppose I have a container of fluid. I'll just use blue, often talk about water. And I want to submerge some object in it. So if I do, it's going to displace some water. So let's just talk about the water first. So if I have a cube of the fluid, I'll use water, but this could be any fluid. I'm going to just speak of it as water. We know that there's going to be some pressure at the top that I'll call P0. And then the pressure at the bottom is going to be P0 plus rho GH, okay, where H would be the height of this block of water inside the water. Now, the block will have an area on top and bottom that's equal of A. And so if I want to find out what the net force due to the water alone, so what's the water doing to this block, I could say, well, there's going to be a force at the top, I'll call F0, which is going to be equal to the pressure at the top times area. And there'll be a force at the bottom, okay, that's going to be equal to the pressure at the bottom times A. So distributing that A through, I get this, rho GHA, okay? And so I can find what is the net force from the water, so not net force from everything like gravity, but net force from the water upward, and we call that the buoyant force. That's just going to be equal to FB, which holds it up, minus F0, which is at the top, and so that's going to be rho, or P0A plus rho GHA minus P0A, okay? So again, this term right here is at the top, and then this term right here is at the bottom. Okay? So you can see clearly that the top pressure doesn't matter, and we get that the buoyant force is equal to rho GHA or rho GV, which I'm going to write even one more time of rho VG. Okay, and so that's the whole net force from the water acting on that cube of water. And now, if the object was just water, just the same fluid, or at least, then we'd get that the net force on it, so F net truly, the true net force, is going to be this buoyant force minus the force of gravity acting on that. So that would end up being rho Vg minus, and knowing that mass, this mass here, is going to be equal to the density of the material in the cube, or in the block, times the volume of that block, and then times the G. We can see that if it's a block of water, we get no net force. But we can now generalize this. What if it wasn't a block of water? Okay, everything else about it was the same. The pressures are the same. It's just depending on the depth of the water. So I can put some subscripts here and go F and maybe material here. And I can emphasize that now what I know about whether it's going to be a net upward force and net downward force, I can say that's going to be the density of the fluid minus the density of the material, all times the volume of the submerged object times gravity. And so that would tell me that if I place something in the water fully submerged, then I'm going to either have an upward force if, okay, I'm going to upward force if the density of the fluid is greater than the density of the material, so the minus sign gives us a positive. It will sink if the density of the material is greater than the density of fluid, that gives us an overall negative. And it'd be neutrally buoyant if the density of the material is equal to the density of the fluid. So this allows us a way of determining what would happen. What would be the net force on a fully submerged object? Now, I've been careful to say fully submerged, but because this only applies to if the object is fully underneath the water. So the volume of the fluid that's displaced, giving rise to the buoyant force, so this volume right here, which came from here, is the same as the volume of the material. Okay, but we can also generalize this even further by saying, well, what if the object is floating on top? So we have our container, our water, and our object is submerged only part way. Then we have this area here, and that's the volume of the fluid that's displaced versus the volume that's the entire thing, which would be the volume of the material, the object. Okay, well, we can go to it and just kind of focus on the pressure, the difference right here, the buoyancy force. That's just going to depend on the volume of the fluid. So I can come down here and let's go and skip this one. Come down to F net again and say we have the density of the fluid, the volume displaced of the fluid times gravity, and that's going to have to be offsetting the downward force of gravity, which is the density of the material, the volume of the material times gravity. And this gives us just a different way of looking at something that is floating. So if it's floating on top, so the volumes aren't the same, we know that this equals 0. That's kind of the definition of floating. It's not sinking, it's not rising up, it's floating, so that's equals 0. So that gives us a way of relating the volume displaced from the volume of the object, or we can write it a little differently. We can have that the mass of the fluid displaced, I'll put F comma D, the displaced fluid, times gravity, equals the mass of the material or the object, which is its total, not just what's displaced or what's underneath, times G. G's cancel out, and we can see that the mass of fluid displaced must equal the mass of the object from this derivation. And so that's what we get from the idea of a buoyant force.